Today on Macaulay Math, we're talking integration by substitution. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 25 on integration by substitution. Our goals for today. We're going to use pattern recognition to find an indefinite integral. We're going to use a change of variables to find an indefinite integral. We're going to use the general power rule for integration to find an indefinite integral. We're going to use a change of variables to evaluate a definite integral. And we're going to evaluate a definite integral involving even and odd functions. In this lesson, some of the techniques used to integrate composite functions will be discussed. We will start with a discussion of U substitution, but it will ultimately become a discussion about seeing patterns in the integration so that it will not always be necessary to complete a full formal substitution. Let's start with a demonstration. The antiderivative of a composite function. Let g be a function whose range is an interval I, and let lowercase f be a function that is continuous on I. If g is differentiable on its domain and capital F is an antiderivative of lowercase f on I, then the integral of lowercase f composed with g of x times the derivative of g of x dx is equal to capital F composed with g of x plus some constant c. In U substitution form, what that'll look like is the integral of lowercase f of u du is equal to uppercase f of u plus some constant c. Now, what does all that mean? Well, let's do a little exploration. So the first thing that we're going to do is we're going to take the derivative of this function using the chain rule. And so f prime of x will be equal to, if I bring down the 4, I'll have 4. I leave what's on the inside alone, so it'll stay x squared plus 2. I reduce the exponent by 1, that'll give me a 3, times the derivative of what's inside, that's 2x, and the derivative of a constant is always 0. And then the derivative of this 9 is also 0. And so what we want to note here is that when I do the derivative of a composite function, I get this additional multiplied term here. I end up with a u function here and a differential of that function right there. So here's what happens. When I integrate this function, if I'm doing it correctly, I should get something that looks like this original back out. And so what this expression here says is that if you have the derivative of this inner function, when you go to take the integral of it, that derivative portion disappears. So when I go to do this integration, if I want to say the integral of the 4 times x squared plus 2 to the third times 2x dx, when I go to do the integral of this, I notice that this function here is the derivative of this inner composed function there. And so when I go to do this integral, 4 is a constant, it's left alone. Then I have to go x squared plus 2, since it is a composite function, it must stay in the middle. I have to take this 3 and add 1 to it. We have to divide by 3 plus 1. This derivative of the inner function is going to disappear, and then I'm going to have to add some constant c. The 4 and this 4 is going to cancel, and I'll be left with x squared plus 2 all to the 4th power plus some constant c. The constant c is represented by the 9. So therefore, the integral in this term, the derivative of the inner function, must disappear. We see that in this definition where this g prime function is going to disappear. So what does a full U substitution look like? Well, there is a guideline that we want to talk about. Look for a quote-unquote more complex inner function. And so if I look at this, it's a multiplication here, and we already know from a previous lesson that there is no product rule for integration. But I do see that an x to the third function is composed with the x squared minus 9. Here, my inner function is my x squared minus 9. So what I'm going to do is I'm going to let u equal x squared minus 9, that inner function, and then I'm going to derive this. And I'm going to say it's going to be du is equal to 2x dx. Now, this isn't in any textbook, but the way I think of this is a conversion factor to u. And so if I want to change to a u variable, I have to change to this differential of u. I need this conversion factor from dx to u. What I will do here is I will reorder, and I will rewrite this as x squared minus 9 to the third, and then I'll go x dx. Now you'll notice I needed a 2 here, but we can use a funky 1 to get a constant. And so here's what I'm going to do. I'm going to put a 1/2 out here, and I'm going to put a 2 in there. Now, 1/2 times 2, that's a 1. And so I am not changing this function, because when you multiply a function by 1, you get the same function. I'm just putting it in a way so that I can do my substitute. So here's what I'm going to do. I have my half. I have my integral. This expression right here becomes u. That's what I have here. It's still to the third. And this expression right here becomes du. And now I can integrate this much more easily. And so I'll have a half. I suppose I should have my equals here. Let's not forget that. Half. It'll be u to the 3 plus 1 over 3 plus 1. And then plus some constant c. I can then simplify. And so I will have 1/8, because 3 plus 1 is 4, times 2 gives me the 8. I'll have u to the 4th plus c, and then I will replace u with the x squared minus 9 that I had. So I have 1/8 x squared minus 9 to the 4th plus some constant c, putting in all my equals. And we are good to go. Another example of a u substitution to find the integral. And again, I see a square root function, and I see this 1 plus 4. It seems to be the more complex portion of a composition. So I'm going to let u equal 1 plus x to the 4th. then du is going to equal, well, the derivative of a constant is 0, and I'll have 4x to the third, and then I'll have my dx. So here again, this is my conversion factor, and so I'm going to want to move some things around. So the first thing I'll do is I will rewrite this, and we'll make it 1 plus x to the fourth to the negative 1/2 power times x to the third dx. Now again, I need 4x to the third, but I have just x to the third. So again, I'm going to use a funky 1 to get the constant. So if I put a 4 there, I have to put a 1/4 out front. And so 4 times 1/4 is 1. I got a funky 1. So now I'm going to do my substitution. I'll have 1/4 integral, and then this thing right here is going to be u. So I will have u to the negative 1/2. This expression here is my du, so I'll have du. And now I can integrate using the general power rule. That will give me 1/4 times u to the negative 1/2 plus 1 over negative 1/2 plus 1, all plus some constant c. I'm going to simplify this. That'll give me, let's see, so I'll have a 1/4 divided by a 1/2. That'll give me a 1/2. And then it'll be u to the 1/2 plus c. And then we will substitute u equaling to 1 plus x to the fourth. And so I'll end up with a 1/2 times 1 plus x to the fourth to the 1/2, all plus c. And that will be my final answer. Use substitutions can also be used for change of variables. This is also going to be useful when the integrand is complex and cannot be easily rewritten using simple integration rules. In this particular instance, I would normally say, based on my last two examples, that this 2x minus 1 is the more complex inner function. And so I would normally say let u equal 2x minus 1. But when I do the derivative of that, I'll just get 2 dx. Well, I've got this extra x in here, so I have to do something with that. And so a possible solution to that is to solve this thing for x. So if I bring the 1 over and I divide by 2, if I let x equal u plus 1 over 2, or let x equal half u plus 1/2, and I do the derivative of that, I can say that dx is equal to 1/2 du. And so what this allows me to do is now I have a direct substitution for dx with a constant value. So here's what we're going to do. We're going to do a substitute So I'm going to say that x is equal to, this x here becomes 1/2 u plus 1/2, which is what I had right there. And then the square root, which I'm going to write as a 1/2 power. 2x minus 1, this 2x minus 1 becomes just u. And then what I can do is I can substitute for my dx. So this goes right there. And then my dx becomes 1/2 du. And because I'm directly substituting, I don't have to mess with it this time. Now what I can do is I can factor And so I'm going to factor out a half here. I'm going to factor out this half. So a half times a half gives me a quarter. And then I'll have the integral of u plus 1 times u to the 1/2 du. And now I will distribute. And that will give me 1/4 integral u to the first times u to the half is u to the 3/2. U to the half times 1 is u to the 1/2, all du. And now I'm going to integrate. And we're using the simple power rule on each of those. So I leave my 1/4 out front, put a box there. And so this becomes u to the 3/2 plus 1 over 3/2 plus 1 plus u to the 1/2 plus 1 over 1/2 plus 1, all plus some constant c. And so let's simplify a little bit. Let's make it 1/4. This becomes 5/2 because 1 is 2 over 2 plus 3/2 is 5/2. When I divide by 5/2, that's like multiplying by 2/5 u to the 5/2. Similarly, half plus 1 will be 3/2, so I'll have 2/3 here, u to the 3/2 plus some constant c. I have to distribute this 4. So here we'll distribute and substitute u equals 2x minus 1. And then, so 4 times 5/2 will be 1/10. And then it'll be 2x minus 1 to the 5/2 plus, again, when I multiply 1/4 times 2/3, I'll get 1/6 times 2x minus 1 to the 3/2 plus some constant c. Now, I'm sure that we could simplify this a little bit, but for the sake of this discussion, we'll leave it like that. And I'll say if you're taking a test from me, I would accept that as a final answer. Just some guidelines for making change of variables. Choose your substitution u as g of x. Usually best to choose the inner part of a composite function, such as a quantity raised to a power, which is what we've done. We're going to compute du, which will be the derivative of that inner function with respect to x. Rewrite the integral in terms of the variable u. We've done that. We'll find the resulting integral in terms of the variable u. And then we'll replace u with g of x to obtain the antiderivative in terms of x, and then we'll check our answer by derivating. Now, for definite integrals, which I'm going to show an example of here, we can skip steps 5 and 6 by finding new upper and lower bounds with an equation for u. So what would that look like? All right, so here I have a integral. It's the same integral that we just did, but now it's a definite integral with an lower and upper bound. So we're going to do essentially the same process, but we're going to do the integral with new limits of integration. So again, I'm going to say my du is going to be equal to 2 dx. Remember, our x was equal to 1/2 u plus 1/2, and we had our dx equaling to 1/2 du. Here we're going to do that substitution. In the same way that we did before. So it's the integral. The x becomes 1/2 u plus 1/2 times u to the 1/2 power. And then we have times 1/2 du for that substitution, just like we did in the previous example. But here I have to change the limits of integration. So what I'm going to do is I'm going to plug 1 and 2 into this equation and get new limits of integration. So u times 2 times 1 minus 1 is equal to 1. And then u equal to 2 times 2 minus 1 is equal to 3. So this is my new lower limit. And this is my new upper limit of integration. And what that's going to do for us is I'm going to be able to go, all right, from 1 to 3 now, instead of 1 to 2 in the original, I'll have this half u plus 1/2 times u to the 1/2 times 1/2 du. And so we'll do the same thing we did in the last one. We'll move the half one, we'll do it in just one step. We'll move the half out and we'll move the 2 halves out front, and then we'll distribute the u to the 1/2. And so what we'll do here is we will simplify. And since I've already done this once, we'll skip a few steps. We'll factor out the half and we'll bring that half out front. We will bring the half out front from there and this half out front to give me the 1/4. We'll keep our new upper and lower limits of integration, and we'll distribute this half to give us u to the 3/2 plus u to the 1/2 du. And so here we will use the simple power rule. And that'll give me 1/4. And then using the information from the last example, it'll be 2/5 u to the 5/2 plus 2/3 u to the 3/2. And that'll be evaluated from 1 to 3. And so now what we have done is now, because of the new limits of integration, we do not have to resubstitute for u equaling to 2x minus 1. And we can just plug in our new limits of integration. So we can go, I'll distribute that 1/4, and it'll again be 1/10 times 3 to the 5/2 plus 1/6 times 3 to the 3/2 minus the quantity 1/10 1 to the 5/2 plus 1/6 times 1 to the 3/2. Since we're taking roots of prime numbers, we end up with irrational solutions. So I'm just rounding here, 2.158. Well, that's all I got for today, folks. So, the Marvel fun fact of the day: in Star Wars Episode 1, The Phantom Menace, Darth Maul was cut in half by Obi-Wan Kenobi in the climactic final lightsaber battle and thrown down an energy shaft. But his death was never shown, so in the Clone Wars, Maul was brought back as a man who had used the Force to create a new body, including spider legs, which looked pretty cool because they look like those spider legs. Pretty awesome. Again, if you don't see them die in the movies, they're not dead. Well, that's all I got for today, folks. Have a good day. Bye.